Good afternoon, we are Biel Serracanta, Joan Soler, and me, Albert Massana, and we are going to present our solution to problem 7.21. The statement of the problem says, an alternating current source with variable frequency, an inductor with inductance L, and a resistor with resistance R are connected in series. The graph below gives the modulus Z of the impedance of the circuit versus the driving angular frequency omega. We are asked to calculate R and L. Before solving the problem, we need to know the relation between impedance, resistance, and reactance. Impedance can be defined as the amount of resistance that a component offers to current flow in a circuit at a specific frequency. Using this interactive circuit, we can see how to calculate impedance. We can change the values for frequency, resistance, inductance, and capacitance to see how this affects impedance. You have to pay special attention to this diagram. Resistance and reactance are plotted as vectors on a phasor diagram. The resistance is plotted along the x-axis, parallel with the current to show that there is no phase difference between the current and the voltage in a purely resistive circuit. The inductive reactance is plotted vertically upwards, as a purely inductive phase angle is plus 90 degrees, while the capacitive reactance is plotted vertically downwards, as a purely capacitive phase angle is minus 90 degrees. The total impedance of all the components combined, Z, is given by the vector sum of all the components, as shown here. Now we can see how impedance is affected when inductance or capacitance increase or decrease. We can see that the minimum value of Z, as far as we do not change resistance, is given when XL and XC are equal. This would give us a vector which has no height and therefore is shorter than any other vector. Finally, let's take a look to the formulas we need to do the exercise. From this graph, we have to extract that X, the reactance, is equal to inductive reactance minus Xc, the capacitive reactance, and therefore Z is equal to plus the square root of squared R plus squared X.
Okay, now that we have a deeper understanding of the formulas, let's begin to strike problem 7.21, where we're asked to find the resistance and the inductance of an alternating current system. As data, we are giving this graph where there's the modulus of the impedance of the system against the angular frequency. Okay, we know that the modulus of the impedance of the system is just going to be this formula right here for this type of systems, where it's the square root of the resistance plus the square root of the angular frequency times the inductance. So let's just try and find a point at the graph where we're going to be able to make calculations easier, and that's a point where this term cancels out. And we know this term will actually cancel out when the angular frequency equals 0. If we look at the graph, we can check that this point, the impedance, the modulus of the impedance is actually 40. By using the same formula and cancelling out this term, we can determine that the modulus of the impedance is just going to be equal to the resistance. So we have that 40 ohms are just the resistance, and that's how we found the resistance. Let's now begin to part B, where we're asked to find the inductance. Now that we have solved for the resistance, we can actually just plug any point from the graph into our equation, isolate the inductance, and find what's the result. So let's just do that. For terms of simplicity, while looking at the graph, this was the point that was more obvious for everyone to just grab and plug into the equation, so that's why we're using that point. But I want to clarify that any point from this graph would be as good as that one. Let us proceed to do the calculation. So we know that the modulus of the impedance is actually just 100. that's equal to the square root of 40 squared plus 1500 times L squared. Now we know that L is going to be 61 times 10 to the minus 3 henries. That's equal to 61 microhenries. And that's the result for exercise 7.2. Of curiosity, we wonder what would happen to that graph if we added a 15 microfarad capacitance to the alternating current system. That's what my colleague Joan Soler is going to proceed to calculate right now.
Alright, so in this second part, what we're going to do is check how our graph from the beginning of the exercise, from the statement, will look in an RLC circuit. Remember that we used to have this graph in which only an RL circuit was taking place. Now we've added a capacitance, changing this into an RLC circuit. You might be wondering how we've plotted this graph. We've plotted this graph just by using MATLAB. We've plotted it with this code. You will be able to check it on the PDF. Alright, so once we have this plot, we might be wondering whether it's correct or not. Well, it makes a lot of sense that when omega tends to 0, the impedance tends to infinity. You can check that from the Z formula, since omega is on the denominator, on the XC part, and it is actually can be substituted by 0, this will actually give us an infinite value here, which actually makes a lot of sense. From this graph, though, we cannot see very much where the minimum will be. As we know, the minimum will mean the frequency of resonance. We can now take a closer look on this graph. By taking this closer look, we can now see the minimum of the graph, and we can check that it's located in 1045 radians per second, and it gives us the value of 4 on the y-axis representing the z, which actually makes a lot of sense because the statement said that the resistance was 40. How can this be divided though? We can now divide this graph explaining that in the left of the minimum, the circuit will be capacitive, as XC will be bigger than XL. On the other hand, it will be inductive when XL is bigger than XC. Alright, so as to find these values, what I mean by these values, I mean this 1045 and this 40 value, we've done it by MATLAB as well. You can check that by adding these two commands here, we would be obtaining the values of the frequency and the values of the angular frequency and the Z. Alright, so yeah, there we go. We get this value of 40 and this value of 1045. Alright, now we've also wanted to check what was the value of the frequency of resonance, as this is a matter that can actually matter to us. So what we have done is make a new plot in which the function of Z now doesn't depend on omega, but on the frequency, which has just been multiplying by 2 times p wherever we had omega, and therefore we would be obtaining it as a function of the frequency. We now get that this frequency is minimum at 166 Hz, and it gives us a value of Z of 40. This as well, it does make a lot of sense because it must give us the same value as before. And this frequency, can we check that it is true? Yeah, we actually can, because we before obtained 1045 was the omega. Now by simply substituting this value, we get that this equation is right. Alright, so I hope you enjoyed this video, and if you have any doubts, we will be willing to answer them without any question or without questioning anything. So thank you very much, and see you very soon.